Very good. Good afternoon, everyone. Thank you for coming to hear a little bit about Micronaut. I hope everyone is enjoying JNation this year. So I'll get right to it. So my name is Jeff Brown, and I am one of the co-founders of the Micronaut Framework as well as the Grails Framework. I am a partner at Object Computing, which is the company behind both Grails and Micronaut. Grails and Micronaut, of course, are both free open source software, both distributed under the Apache 2 license. And Object Computing is the company that maintains these both of these frameworks, supports them, moves them forward. We're the folks primarily responsible for keeping these technologies moving forward. I've also co-authored a couple of the Grails books for A-Press, and you see an email address and a Twitter handle there. So please reach out and let me know if there's anything at all that I can do to help you out with anything related to Micronaut, Grails, Groovy, or if you have any questions about object computing. So today, in the time that we've got this afternoon, I'm going to provide an introduction to Micronaut and get a sense for, provide a sense for what the framework looks like, and hopefully inspire you to go want to learn more about Micronaut. So I'm going to start with a little bit of history, as that history relates to some of the design decisions that affect how Micronaut, really they affect why Micronaut exists, and they affect some of the design decisions that we've made when building Micronaut. So I'm going to talk about a little bit of history to provide some context for why Micronaut exists and why it is the way that it is. As part of that history, we'll talk a little bit about some of the challenges associated with building and managing microservice applications, and we'll get a sense for what Micronaut is doing to address those challenges. So to get right to it, a little bit of history. So the Grails framework has been around for over a decade, and the Micronaut team is the Grails team. It's the same group of folks, the same technical leadership since the very beginning. It's the same people, same company behind the technology. So Grails has been around for over a decade. In February of 2008 is when we released Grails 1.0, so more than 10 years ago. And the Grails framework predates 1.0 by more than a year. We worked on it for quite a while before releasing 1.0. And around that time, a lot of folks were trying to build JVM web frameworks. And the reason for that is around that time, so 2006, 2007, kind of the state of the art for building JVM web frameworks would have been Struts 1. And Struts 1 was a nice improvement over what predated Struts 1. So if you were writing servlets directly and implementing do get and do put and all that crazy stuff, Struts was an improvement over that. But it was clear there had to be a better way. Struts didn't cover a whole lot of ground, and doing simple things was fairly tedious in Struts. You had to write several components. There was a lot of config stuff. So it was a nice step forward, but it was obvious there had to be a better way. So much so, it was so obvious that around that time, lots of folks started trying to build JVM web frameworks because it was clear that there had to be a better way. When I very first started telling people that we were building this JVM web framework, but well before we got to 1.0, a really common question that folks would ask is, do we really need another one of those things? It seemed like everybody and their brother was making a JVM web framework. There were lots of them emerging around the same time. And the reason for that is what I cited. Lots of folks recognized the gap and recognized that there had to be a better way. So a lot of folks were trying to build JVM web frameworks around the same time. Most of those frameworks never got any traction, never had really any success, but some did. And of the frameworks that did have some success, some of them had varying levels of success and levels of longevity. The Grails framework, more than a decade later, is still very vibrant, still a very important part of the industry. We've still got a successful business built, a successful and growing business built around the technology. Grails is still very much an important part of our industry. And an important part of how Grails has stayed relevant and stayed successful for as long as it has is the fact that the framework has evolved a lot. We have changed Grails a lot since Grails 1.0. One example of that is REST. So in 2007, certainly the idea of REST existed, and people built REST services, but REST was nowhere near as important a decade ago as it is today. Today, every enterprise builds REST services. So you could build REST services with Grails 1.0 for sure, and we did that, and we had success with that. But if you're building REST services with Grails 1, you might have to write a good bit of tedious code yourself. You might have to write some custom data binding and some custom JSON marshalling, because the framework really wasn't optimized or designed for building those kinds of applications. It definitely could be made to work, but it wasn't. There wasn't a whole lot of support in the framework for building REST services. And then over the years, as REST became more and more important, Grails kind of stayed ahead of that by introducing more and more capabilities for building those kinds of applications. And in Grails 3 and Grails 4, the latest versions of Grails, we've got really great support for building REST services. So that's an example of the technology evolving over the years to adapt to the way that people want to build applications today. Another example of that is Gorn, the ORM tool that's part of Grails, and it's always been part of Grails since the very beginning. Initially, Gorn was conceived really to be a layer on top of Hibernate. Hibernate is the de facto standard, by far the most popular ORM tool on the JVM. So so Gorn was conceived to be a layer on top of Hibernate. And what we wanted to do is we wanted to take advantage of really powerful language features that Groovy had to offer to make it easier to take advantage of everything that Hibernate had to offer with less configuration and less code. And we wanted to add additional capabilities on top of what Hibernate had to offer. So that's what Gorn was initially. And for the first year or two of Gorn's existence, one of the, I think the most highly voted feature request was JPA support, right? People wanted to pull out Hibernate and plug in TopLink or some other JPA implementation. So we recognized that and refactored Gorn and created a JPA implementation. So then you could use Hibernate or you could use any JPA implementation, and that was great. And then fast forward a couple of years past that, and the so-called NoSQL databases started gaining traction. Databases like MongoDB and Cassandra and all of those non-relational databases that started gaining popularity around the same time. As those databases started gaining popularity and gaining traction, folks wanted to use Gorn to interact with those kinds of databases. So we refactored Gorn even more. And today we have Gorn for Hibernate, we have Gorn for JPA, we have Gorn for MongoDB, Gorn for Neo4j, which is a really interesting graph database. We've got a bunch of Gorn implementations for different kinds of databases. And that's another example of the technology evolving over the years to adapt to the way that people want to build applications today. And there are lots more examples like that in the Grails framework, but I'll leave it at just those two. The point being that the evolution of the technology has been an important part of the framework's longevity and continued success. Evolving to stay relevant and stay optimized to support the kinds of applications that people want to build today. Right? That is the reason that Grails is successful 12 years later, and a lot of the other folks are no more. They failed to adapt and recognize things that needed to be recognize things that called for adaptation. That's an important part of Grails' success. One of those changes in the landscape, just like the interest in JPA and the interest in REST services and the interest in other kinds of databases, another one of those changes that's come along in recent years is the interest in building microservice architectures, right? So again, microservices, or at least what we would call microservices today, certainly those things existed a decade ago, but they were nowhere near as important, nowhere near as big of a deal as they are today. There are a bunch of microservice talks here at this conference today. Microservices are very important. Lots of enterprises are in the process of migrating their systems to microservice architectures. Lots of enterprises have already done that. Lots of enterprises are about to do that. Microservices are an important part of our industry landscape right now. It turns out that Grails is not a terrific fit for building microservice applications. And we recognize that. And I've got time to talk a little bit about why that is. But Grails is built on top of the Spring Framework, and the Spring Framework is terrific. There's all kinds of really great stuff that Spring has to offer, and that's why we built Grails on top of the Spring Framework. So every Grails application is a Spring application because we're built on top of Spring. So anything you can do in Spring, you can do in a Grails app, and then we add a bunch of capabilities on top of that. But these frameworks, Grails and Spring, were never designed for building microservices. Absolutely, you can build microservices with Grails, and you can build microservices with Spring. No one is saying you can't do that. But when you do that, compromises are being made because these frameworks were really not designed for building those kinds of applications. And we'll press into that just a little bit. So just like we confronted the growing interest in REST and the growing interest in these various kinds of data stores, we've got to address, or we had to address, this growing interest in building microservice applications. So one of the things we could have done is we could have continued to evolve our current technology to be more and more compatible with building microservices. Or we could go back to the drawing board and design a thing from the ground up specifically for building microservices. And that's what we've done, and that's what Micronaut is. So we started development on Micronaut almost 2 years ago. It was the summer, later part of the summer in 2017. So we're coming up on a couple years ago is when we started development. And early on in that process, one of the things we had to do was develop an understanding of what did we want this framework to look like? What are the attributes or the virtues that we want the framework to prioritize? So we came up with a list of goals. And the list is long, right? This is a small subset, but these are a few things that are kind of easy to think about and easy to talk about. But we wanted the framework to have really fast startup times, really small memory footprints, small executable jar files, minimal dependencies on other frameworks. So we had this list of goals for the framework that we wanted to build. And a lot of these goals, or a lot of these things relate to microservices in ways that are different than how they relate to monolithic apps, which is really what frameworks like the Grails framework, or applications like that are really well suited for building with frameworks like Grails. So if you're building a monolithic web app, Grails is a fantastic fit for that. These are attributes that affect monoliths in ways that are different than how they affect microservices. For example, your memory footprint, right? When you deploy a Grails application, you might allocate a small Grails application, you might allocate 500 meg of heap to the thing. And a realistic application that's doing a lot of stuff, you might allocate a gig of heap, or maybe 2 gig of heap, maybe even more. But that puts you in a ballpark of how much memory you're probably going to allocate to a monolithic web app like that. So call it a gig of heap. For a monolith, maybe that's not that big of a deal, right? You set up your Tomcat instance or whatever serverless container you're using, you allocate the memory there, you deploy the WAR file to the container, and the thing's up and running. And so maybe you don't think too much about that gig of RAM. Maybe it's not that big of a deal. And in your development environment, maybe it's not that big of a deal. You run the scripts to start the program up to support your development work, and maybe you don't even recognize what's happening. But maybe the startup scripts are allocating a gig of heap to the thing so you can run it. But it's really just not that big of a deal. It's not that painful. Most folks don't even notice it, but it's a cost that's down there that you don't recognize. And that's okay for building a monolith like that. But if you're building microservices, often there's not one thing, right? There's lots of things, these things communicating with each other. It'd be great to be able to start up a bunch of those concurrently on your development machine. So if you wanted to start up, say, 20 different microservices on your development machine concurrently and have them communicating with each other, if you had to allocate 2 gigabytes to each of them, you're not going to be able to do that. That's going to fail for a number of reasons, and one is you're going to run out of memory. And not only in your development environment is that a concern, but also in your deployment environment. Often when folks are building microservice architectures, they want to deploy them to these really robust cloud platforms like GCP, Google Cloud Platform, or AWS, and take advantage of all these great services that the cloud providers have to offer. And when you do that, when you deploy your microservices to GCP or AWS or any of the other cloud providers, How that pricing model works is your cost is affected by things like how many VMs do you need? In the VMs, how many processors do you need? How much memory do you need? How much disk space do you need? All those things factor into your cost. So the memory affects the cost of your production runtime environment. So if you've got to deploy 40 services and allocate 2 gig of RAM to each of them, and maybe you've got dynamic scaling going on, and maybe it's not really just 40 services, it's 40 services, but maybe some number of instances of every one of those services. You've got a lot of VMs, a lot of stuff going on out there, a lot of memory. That cost adds up and becomes significant. So we had this list of goals. We want really small memory footprints. We want really fast startup times. And that helped us move forward with the process. So one of the things we had to do once we had a pretty good list of goals is we had to relate those goals to our current technology and develop an understanding of why can't we satisfy those goals with our current tech. And the point of that exercise was to help optimize the solution that later we would end up building. So for example, we had to ask questions like, why can't I run a Grails application in 12 megabytes of heap? And why can't I start a Grails application up in 900 milliseconds instead of 30 seconds, right? A whole different ballpark. So a typical startup time for a Grails app might be 20 or 30 seconds, depending on a bunch of factors, but that puts you in the neighborhood. So say startup time is 20 or 30 seconds. So we wanted to target startup times that are sub-second or around a second, sort of a whole different ballpark. So why can't we start a Grails application up in less than a second? Why can't we run a Grails application in 12 megabytes of heap? And on down this list of attributes, or a list of goals that we had. So we developed a list of goals, developed an understanding of why we can't satisfy those goals with our current tech, and then we're ready to start charging forward and building this thing. But as we were looking at the reasons that we can't satisfy those goals with our current technology, the answers for all the different things in that list are different. But a lot of them have to do with how Spring works. So as I said, Spring is terrific. There's all kinds of great stuff that Spring has to offer. The Spring programming model is great, right? Things like in Spring, you can write a class and annotate that class with @transactional. And now a bunch of really great behavior is added to that class for you. You don't have to write the code. Spring adds this behavior to your class for you. So when you call one of the methods on that class, a transaction is already automatically started. And when the method returns, the transaction is committed. And if an exception is thrown, the transaction is rolled back. And there's more to it than that. But the point is that there's a bunch of great behavior, valuable behavior that you get by simply annotating your class. And Spring is providing all that. That's really powerful. It's really valuable. That's awesome. The programming model is awesome. The problem with all that is the way that is carried, the implementation details of how that's carried out. So one of the things that Spring has to do at application startup time is it has to read the bytecode for every class that's in the application context, and that can be expensive. And the more code you have, the more expensive it is, because it's that much more bytecode that the framework has to read. It has to look through all that bytecode and look for annotations and understand some things that will help Spring initialize the Spring application context. And then later on in that process, Spring has to do a bunch of runtime reflection to look at annotations and figure out where your dependency injection points are, figure out where things like transaction management needs to happen, where dynamic proxies need to be created to support that. There's a lot of stuff going on that relies on reading your bytecode and doing a lot of runtime reflection to create dynamic proxies and so forth. And that's where a lot of the expense comes from that keeps us from satisfying a lot of these goals that we had in the list that I talked about before. So the programming model is awesome, right? The fact that you can write a class and annotate it with transactional, that's great. But the cost is prohibitive or problematic for microservices in particular. So we recognized that and thought that there has to be a better way. So that's when, then we started charging forward, actually building the Micronaut framework. So as I said before, we started development almost 2 years ago. Last May of 2018, so just about a year ago, is when we released the first milestone of Micronaut. That's when the framework was open sourced, and that's the first time anyone outside of object computing got to see the thing and start playing with it. So last May was May of 2018 is when we released Milestone 1. October of 2018 is when we released Micronaut 1.0 GA, so that was really the official release. And since then, we've had quite a few releases. We've just recently released Micronaut 1.1.2. We're working on Micronaut 1.2 now. So a lot of development is going on. The runtime in Micronaut is really lightweight and really fast. Our runtime is based on Netty, not Jetty with a J, but Netty with an N. And one of the things that's interesting about the runtime, the Netty-based runtime, is with Micronaut, what we've done is we've kept the framework separate from the runtime, which we did not do with the Grails framework. With the Grails framework, the framework is pretty tightly coupled to the servlet API. The only way to run a Grails application is in a servlet container. There are no exceptions to that, and there have never been any exceptions to that. Every Grails application that has ever ran in a servlet container. And we didn't want that same kind of relationship between the framework and the runtime with Micronaut. So we've kept those completely separate. The runtime, the default runtime that's there now is based on Netty, which is really fast. It's really lightweight. It's got a bunch of reactive, there are a bunch of great capabilities that Netty has to offer that justified why we built our runtime on top of that. But that runtime is fully pluggable. So we can plug in a gRPC runtime. Eventually we'll build a servlet container runtime that you can plug in. But most of the capability of the framework is above that and is separate from the runtime. So the runtime is pluggable in the framework. We're positioned to support other runtime environments in the future, and that's great. And that wasn't by accident. That was all thought out ahead of time, and we're in a great position with respect to that. Micronaut is not really just one thing. Micronaut is really a portfolio of things that help you build microservice applications. Among those we've got an integrated aspect-oriented programming engine. We've got a really robust and really interesting dependency injection container. Our DI container is a few interesting aspects of our DI container include that our DI container is fully compliant with JSR 330, which is the dependency injection specification. Our DI container passes the full TCK, so every JSR has a technology compatibility kit, which is basically a test suite that will test your implementation and let you know whether or not you're compliant with the spec. So our DI container passes the full TCK, so it's a fully robust dependency injection container. And it's usable separate from the rest of Micronaut. So if you were building an app that's not a Micronaut app, just some JVM application, and you wanted to use a dependency injection container, you can use Micronaut's DI container without bringing in any of the other Micronaut stuff. So the DI containers really is a standalone thing that can be used separate from the rest of the framework. And one of the really interesting things about the DI container, and really valuable things about the DI container, is the fact that we don't do any runtime reflection in order to, in the implementation of the DI container. So the DI container is fully configured at compile time. So at compile time, we recognize where all the annotations are, where all the injection points are, where proxies need to be created, where AOP needs to be applied. All that is sorted out at compile time, which makes the runtime really, really fast and have really, really small memory requirements. The DI container is both of those things, really fast and doesn't use a lot of memory. The DI container is one of the things that is sort of easiest to recognize about one of the things about Micronaut that's really easy to recognize how cool that is. So lots of folks are so everyone uses the DI container in Micronaut apps, and then more and more folks are using the DI container outside of Micronaut apps, just some other app where you want a DI container. So the fact that we're not doing any reflection there is a really big deal. So in addition to an AOP engine and a DI container, Micronaut also includes a really interesting HTTP client, which is an important part of building microservices, right? In a microservice architecture, you've got lots of processes out there all communicating with each other. And so a request comes into the system and hits component A. And component A calls component B, and component B calls component C, and that thing talks to the database. And that's how microservice architectures work, right? You've got all these nodes communicating with each other. In every one of those communications, you've got a client and a server, right? The request comes into component A. A is the server that received that request. When A calls B, A is the client and B is the server. And when B calls C, B is the client and C is the server, and so forth. So the HTTP client is an important part of Micronaut, and I'll demonstrate some of the capabilities that the client has. But Micronaut recognizes that microservice architectures include both clients and servers, and we've built a really, really robust, really interesting HTTP client to address that. So what I want to do is I want to write a little bit of code to demonstrate some really cool capabilities of Micronaut. So I've just created a brand new directory called JNation, and what I'm going to do is I'm going to create an application, and I'll say that this application is going to use a couple of features, and I'll call the app JN Demo. So the features that I'm adding to the app are Spock and Discovery Console, and both those we'll talk about and understand why I want them there. And the application, again, is called JN Demo. So let's load that thing up in the IDE and see what we've got. And one of the things that you'll notice is in this project is a Gradle build, right? So there's a build.gradle file and there's Gradle wrapper files. So by default, we create a Gradle build. But if you prefer Maven, when you create the application, --build Maven demo, you can specify that you want to use a different build tool. In particular, you can specify that you want to use Maven. And if we looked, I'm not going to load it up in the IDE, but if we look at that newly created project, there's no build.gradle and no gradle.w files. There's a pom.xml and some maven.w files. But Micronaut supports, really we support any build tool. You can use whatever, you could write your own build tool and build Micronaut apps with it. But we've got support for generating a Maven build or a Gradle build, and Gradle is what we build by default. All right, so I want to quickly get some code in this project. We're starting completely from scratch. There's no code in place ahead of time. So I'm going to write, we're going to start with a really, really simple hello world kind of example. And even with that hello world example, we're going to be able to explore some interesting capabilities that Micronaut has to offer. One thing in particular that I'm going to keep very simple is in this controller, we're not going to have much complexity. I'm going to keep this thing really, really simple. There's a lot of cool stuff that you can do in Micronaut controllers, but that's another talk and not what I want to focus on today. So I'm going to keep this controller really, really simple. We're just going to pass a string in and return a string. There's a lot more interesting stuff we can do in a controller, but as I said, that's not what I want to focus on today. So that's a simple controller in a Micronaut app. Let's run the app. Before I run the app, I have to get one thing running here that I'll talk about in more detail after we take a couple more steps with our app. But I need to have console running. We'll get back to that and understand what that's all about before we're done. So back in our newly created project, so I created the project and added just this Java code. So a very simple controller with a simple endpoint on it. And we're going to use that as our starting point. Let's see what that does. So if I send a request to localhost 8080/hello/Jeff, you see we get a response, hello Jeff. So whatever I specify is the last part of the URL there. What just happened there? My thing. Whatever I specify is the last part of that URL gets passed in. I had a problem with console there. Gets passed into our controller action as a method parameter, right? So this method in the controller is annotated with @get, and then I've specified a URI there. What that means is anytime I send a request to a URI that matches what I've expressed right here, if the request is a GET request and the URI matches that, this controller action gets executed. And then we've got some stuff that'll find this value and pass it as an argument into your method. But if I send a GET request, excuse me, to /hello/something, this controller gets executed. And that's our starting point. So I want to add a test to this project, which is going to enable us to explore some of the stuff I want to focus on this afternoon. So I'm going to use Spock to write this test. And remember that when I created the project, I specified two features that I wanted to use. I wanted to use Spock, and I wanted to use Discovery Console. The effect of specifying that I wanted to use Spock was really just the Spock dependencies were added to my build.gradle file. And so I want to take advantage of Spock to write this test. So let me put a little bit of code inside of this test. And before we're done, you're going to understand what all this code does. But let me get the thing operational here. There we go. That's just some test setup that we need. And what I'm going to do now is, in this test, I'm going to send a request to the application and verify that I get back the response that I expect to get back. So if I send a request to /hello/Jeff, I expect the response to be hello, Jeff. Before I run this test, one thing that I'm going to need to do in the IDE is enable annotation processors. And the reason for that is I mentioned before that Micronaut, our DI container, for example, doesn't do any runtime reflection. So it's all configured at compile time. And I'm going to talk a little bit more about that later. But for now, know that excuse me, the way that works is we have compile time annotation processors that generate a bunch of generate code for you. And in order for that to work, annotation processors have to be enabled. If you're building from the command line using Maven or Gradle, you don't have to worry about it. The correct thing will happen. But when building from IntelliJ, I need to turn on annotation processors so our annotation processors get executed. So if I run this test now, and so let's talk about what's happening here while the test is starting up. So on line 14 there, what's happening is that is starting up the whole server. It's not creating any mocks or a stripped down test environment or anything like that. It's starting up the entire application. So everything in the app is up and running at that point. And because the startup time is so fast, it's practical to do that. You can start up the whole server when you run your test. It's not the case that in every test you want to do this, right? Lots of tests will be unit tests and you'll create your components and interact with them and you don't need the whole server running. But for functional tests, when you do want the whole server running, it's totally practical to do that in a test. In fact, we've got a testing library that makes this even easier. So you can get rid of this code and just annotate the class with @Micronaut test, and there's a bunch of great stuff in that testing library, but not what I want to press into today. So that's starting up the server, right? And when you start up the server in a test environment like this, the server is going to start on a random port, and so you don't know what port it's going to start on. One of the things I can retrieve from the embedded server object is the URL at which it's running. So embedded server.url is going to be something like localhost : some port number. And what line 17 is doing is creating an HTTP client for sending requests to that destination. And this is one of the things I want to focus on. We're going to learn some really cool stuff that Micronaut supports around HTTP clients. But I'm going to start with this kind of lower level HTTP client, and then we're going to get to some really cool stuff before we're done. But this is creating a client that will make requests to whatever URL the server is running at in this test environment. And this, I don't want to spend a whole lot of time here because this is what we're going to improve. But in short, just what I'll say is going on there is we're sending a GET request to /hello/Jeff and verifying that the response is hello, Jeff. That's what I want to improve on. All right. In order to do that, what I want to do is I want to come back to this controller. And I'm going to introduce another component into the mix here. And I want to call this component, we'll say, greeting helper. And in the greeting helper class, I'm going to add a method that I'll call create greeting. And you pass in a name and you get back a greeting, right? So we'll say that's our greeting. And imagine this is complexity, right? This is your business logic. We're making REST calls and we're doing complicated math and we're talking to the database and doing machine learning. So we've got a lot of interesting stuff going on here. That's what you're pretending about this code. This is complexity. This is your business logic. And I want to get that complexity out of this controller, right? I don't want that logic here. I want it someplace else. That someplace else is the greeting helper. So what I'm going to do is add a constructor to this class that accepts a greeting helper as a parameter, just like that, right? And at compile time, our annotation processors will recognize that constructor is there and will generate the instructions. Again, at compile time, we'll generate the instructions that it takes to create a hello controller. And those instructions know that we're going to have to pass the greeting helper bean as an argument to the constructor here. So the greeting helper bean will have to be created, initialized, and ready to go. And then we can create the hello controller. That's not unique about to Micronaut's DI container. That's how you can do the exact same thing in Grails. You can do the same thing in Spring. You can do that with lots of DI containers. What's unique and innovative about this is how we're doing that. And again, we're doing it all at compile time, which means no runtime reflection. No runtime reflection is used to discover that this constructor is here. Right? That's all sorted out at compile time. That's good. And I want to delegate to that greeting helper here like that. And I'm going to run my test again, and I expect the test to fail right now. There are two reasons that the test is going to fail. We're going to stumble over the first one, we'll fix that, and then we'll get to the second one. So the first reason the test is going to fail is we can't create the controller because there is no greeting helper bean. Right? So in the controller, I expressed that the greeting helper bean needs to be passed here. There is no greeting helper bean. The reason there is no greeting helper bean is I only did part of the necessary work here. I wrote the greeting helper class, but what I didn't do is express that I want an instance of that class in the application context. So a way to express that is to annotate this class with @singleton, and that will cause an instance of this class to be created and added to the application context, and now it can be injected into any other beans, including our controller. Notice that the message that I created here is, well, hello there, Jeff, or well, hello there, someone. And I did that on purpose because I want to see the test fail because of that message, just because it's not a good idea to ever trust a test that you haven't seen fail for the expected reason. Right? So this right here tells me what went wrong that time. I expected hello, Jeff, but instead I got well, hello there, Jeff. So let's fix our test expectation. And now we should be in business. So I'll run that test again. And we see, so what we're seeing right now is the DI container at work, right? The DI container created a greeting helper for us and injected it into the hello controller, and this controller can use that greeting helper. All right, so far so good. Now we get to do some really cool stuff. So I'm going to create an interface that I'll call greeting client, and I'm going to annotate that interface with Micronaut's client annotation. So here is where you see the import statement for the client annotation. That's a Micronaut annotation. And this is how, I'm doing this in the context of a test, but this is how you write HTTP clients in a Micronaut service. And this is really, really cool. Follow along and make sure this makes sense. So what I've got is I've got an interface annotated with that client, and I'm specifying a slash here. We're going to get to that. But I've annotated this interface with that client. In the interface, I can define any number of methods I like and annotate those methods with the same annotations that I can use in a controller, like @get, @put, @post, @delete, so forth. And what will happen with this is we're not going to write a class that implements this interface. What's going to happen at compile time, Micronaut is going to create a class, a .class file, that represents a class that implements this interface. And in that class is going to be a bunch of cool behavior. And we're going to be able to press into just a little bit of it. And I want to interact with that thing from this test. So let me change a couple of things here. Application context, get bean, we'll do that. And then I'm going to leave that there for reference, but I'm going to comment it out. Client.greet Jeff. All right. So now, up at line 19, instead of calling HTTP client.create, instead of doing that, what I'm doing is I'm retrieving a bean from the application context that is a greeting client. That bean will be something that implements this interface, and that something has a bunch of powerful behavior in it. So this is what an HTTP call looks like in a Micronaut service. So when I invoke that greet method, what's going to happen is an HTTP request is going to be sent someplace. And we don't know the machine name or the port number yet, but below that, so it'll be some machine name, some port number. Below that will be /hello/Jeff, because I'm invoking the greet method here. The greet method is annotated with @get. So the result of invoking this method is a GET request is generated to this URI at whatever server this client is configured to work with. And that's where this slash comes into play. We're going to see a few things that I can put in where you see this slash. So what the slash means is this client will be configured to make calls to whatever server created the client. right? So here we're starting a brand new server, and here we're retrieving the client from that server effectively. So the client, because I've got a slash here, will be configured to send requests to this server, right? The server that started the server that created that instance of the client. So let's run this test and verify that works. Yeah, so it looks like it did. So we're going to come back to this, and we're going to break this in an interesting way. So let's go to our greeting helper and do this. Let's add a constructor to the greeting helper, and I'm going to inject that embedded server that we saw mentioned in the test. I'm going to inject that into the greeting server, and the reason I want to do that is I want to be able to ask the server what port it's running on. So normally you wouldn't do this in a service, but before I'm done, you'll see why I want to do this here to help demonstrate some capabilities. But so now this greeting is creating this greeting helper is creating a greeting that is something like, well, hello there, Jeff, from port something. All right, so let's run our test, and the test should fail because the test expects the message to be, well, hello there, Jeff, but instead it's going to be, well, hello there, Jeff, from some port number. Right here we see evidence of that. So it was port number 46593. Right, and if I run it again, of course, it'll be some different port number. So one way to satisfy this test would be to, instead of saying that this should return, well, hello there, Jeff, I could say that whatever it returns should start with, well, hello there, Jeff. Or maybe I could do some regular expression stuff. But instead, what I'm going to do is this. I'm going to say when I call that method, whatever it returns, it should return the same thing every time I call that method, assuming I pass the same parameter. And again, this is a funky thing to do. You would never really do this in a test, but this is going to help me demonstrate what I want to get at here. So that test passed, all right? So when I call greet and pass Jeff as a parameter, what's returned is the same thing that's returned when I call greet and pass Jeff as a parameter. So that should make sense. But we're going to break this in an interesting way before we're done here. All right, let's move away from the test for a moment and notice that when I run the application, there's a couple things I want to notice about running the application. One is by default, the server starts up on port 8080. You see the port number here. So that's good. And I don't see what, bear with me just a minute here. Resources, application YAML, that looks right. Start console back up here. I was seeing error messages along the way coming from console that didn't make sense, but let me restart console and see if things will start behaving here. What is missing here? Let me look at this just a second. I can press on without interacting with console if I need to. No, that looks right. That's good. Why isn't this thing registering itself with console? Build Gradle, 1, 2, that all looks right. Error occurred, registering with console. Something's going wrong with the console registration, but I want to press on without, that's not going to be a blocker for us. So inside of Micronaut, what we've got is, we've got support for all the major service discovery engines. So we've got support for console, we've got support for Eureka, we've got support for Route 53. You can use Kubernetes for service discovery. And this application is configured to communicate, to register itself with console when the application starts up. So I just stopped console. When I run the app, we should see a different failure than we were seeing a moment ago. What should happen is the application is trying to reach out to console at localhost 8500 and register itself right now. And it's run -p. Let me look at that command one more time. Yeah. Oh, I see one problem there. I had the port number wrong. That's what's wrong. I've got 8550 here instead of 8500. I like it when mysteries have explanations, and I don't have to wander around the rest of the day wondering what was wrong there. Okay, so now I'm optimistic the thing will work. All right, and that's what I expected to see. So we see two lines of output here. We see that the server is running, and we see a message that says that the server has registered itself with console. That's what we want. Console does a lot of stuff. We're going to press into maybe the first 10% of it here. But one of the things you can do with console is use it. It's a service discovery engine. So if I open up a web browser and I go look at console, localhost 8500, you see JN demo there. What's happening is when my application is starting up, it's registering itself with console. That's the last log message you see back there in the console. The application is registering itself with console. And what's happening is the app says, hey, I'm here. Here's my name, JN demo. I'm running on this machine on this port number. Right? So I've registered myself with service discovery. Now, some other system in our architecture can reach out to console and say, hey, I want to communicate with the JN demo things. Tell me where they are. And console will say, hey, there's one running on localhost on port, whatever port it's running on. And now that client can communicate with JN demo because it discovered where JN demo is by communicating with the service discovery engine. It might be the case that I want to register multiple instances of the same service with console, right? That's a common thing. You've got redundancy, you've got scaling going on, there are lots of instances up and running concurrently maybe. This number 2 that you see here is twice how many instances are running. So when I start one instance, that number will be 2. And the reason for that is for every instance, there's also a health check node. So if I run one instance, you'll see the number 2 here. If I run 3 instances, you'll see the number 6. But if I tried to run another instance of the app right now, it's going to fail. And the reason it's going to fail is the app is trying to connect to port 8080, and there's already something listening on port 8080. So this one, the one I'm running right now, is going to fail with an address already in use, right? So there's a config file. There's a number of ways to configure the port number that you want the app to run on. One is in application.yaml. So if I set micronaut.server.port to be 8086, when I start up the app, it should start on port 8086. Right, and it did. You see the port number there. So it registered with console and said, hey, I'm here and I'm running on port 8086. But I want to run these services on a random port number. And the way to make that happen is you can set the port number to be -1. So I'll start up an instance and it'll start on some random port, 12155. Now I'll start another instance and yet another instance. So I want to run several of these concurrently. One's on 12155, this one will start up on a different port number, and this one will start up on a different port number. And when we go look at console, what we'll see is right now 2 of them have registered themselves so far, now 3 of them have. So there are 3 instances of JN demo registered with that console. I'm going to leave those running for a moment and go back to our test. And I want to talk a little bit about what I can put here that will relate to what's going on in console. So the slash here indicates that this client should be configured to make calls to the server that created it. Another thing you can put here is a URL, right? So you can put someplace.com, and now when I interact with this client, the request will go to someplace.com/hello/Jeff. But that's not what I want. What I want to put here is a label that is the name of a remote service that I want to dynamically discover where that service is. So now when I run this test, we've just broken the test in an interesting way. The test should be broken anyway. We'll see here. What we're going to see is that this is evidence of some really cool capabilities going on in the HTTP client. What's happened is those 2 requests up here on line 24, those 2 calls to the greet method, they were handled by different instances of the service on the back end. So we retrieved a client from the application context on line 19, and then on line 24 we start interacting with it. And what's happened is when the client was initialized, it reached out to console and asked, hey, where are all the services with this name? And console said there's 3 of them. They're all running on localhost, and here are their port numbers. So now inside the client, or the client knows about those 3 remote instances. So all the service discovery stuff, you didn't have to write any code to make that happen. Micronaut takes care of that for you because of this. That's one of the benefits that comes out of this @client annotation. So now the client knows about all these remote instances, and in the client is built-in client-side load balancing. And that's what this failing test is evidence of, that we're round-robining through all the remote instances that we discovered. So in your application, this is what an HTTP call looks like, right? So there's no service discovery, there's no retry logic, there's no round-robining, all that stuff is built into the client. And there's a whole bunch more going on in the client. We've got support for failovers and circuit breakers and retry lot. There's a bunch of stuff in the client. We could spend a few hours just talking about the HTTP client. I just wanted to demonstrate the client-side load balancing and service discovery stuff that's going on there. So hopefully you're able to follow all that and all that makes sense. So just really quickly, we've got about a minute or so. So this is a Java controller that is pretty much what I just wrote interactively. But recognize that Micronaut is a polyglot framework. So we support Java. We also support Groovy, and we support Kotlin. So you can mix and match those languages. You can have one project that has Groovy, Kotlin, and Java in it, and all the stuff. The dependency injection container works in all directions. To put some numbers on some of those attributes I mentioned earlier, so a small hello world jar will be about 8 megabytes, and then depending on what you add to it, it might get bigger than that, but that represents kind of the tax that the framework adds to your application. You can run a Micronaut service in as little as 10 or 12 megabytes of heap, and depending on what your application is doing, you might need more than that, but that puts you in the ballpark. And startup time around a second, and a lot of that has to do with the lack of reflection in the framework. And just one last couple of comments that I want to make is inside of Micronaut. So we've seen there's some service discovery support. We support lots of service discovery engines. We've got great support for configuration sharing, like with Amazon's parameter store, and you can use console for distributed config sharing. We've got client-side load balancing in the client. We've got support for AWS Lambdas and serverless computing. You can deploy Micronaut services to Google Cloud Run. That all works great. So inside of Micronaut are all these great integrations with to take advantage of cloud services. Services commonly part of a microservice architecture. And this tweet, this is the last thing I've got time to talk about. This tweet was posted, I think, before we even released 1.0. But I found this interesting because this fellow is recognizing one of the things that's really valuable and really powerful about Micronaut. So he says it's easy, it's extremely easy to get started to connect to things like Kafka and Zipkin and Consul and Mongo and JPA. And that's one of the things to recognize about Micronaut is it makes it very, very easy to take advantage of these robust cloud services. So all we've seen taken advantage of here in this very simple demo is service discovery and some client-side load balancing. And I've talked a little bit about how our DI container works. There's a whole lot more cloud stuff supported in Micronaut that I just didn't have time to press into today. So I'll leave you with this. Really, if you just remember the one at the top, micronaut.io, if you go there, you can get to all the other places. We've got a terrific user guide at docs.micronaut.io. There's a Gitter channel where you can communicate with the core development team as well as a large part of the Micronaut community. So I encourage you to visit micronaut.io, look at the user guide, look at all the samples. We've got lots of guides at guides.micronaut.io. That's a fantastic resource as well. And I'm over time right now, so I want to wrap it up. But if you have any questions at all about Micronaut or Grails or Groovy or anything we're doing in object computing, please come see me, and I'll be happy to talk with you. But I do want to respect folks' time. So thank you very much for coming, and please come let me know if there's anything at all that I can do for you. Thank you very much.